All right, so this is a continuation of the rotation chapter. And these two chapters that deal with rotation use a lot of what we learned all semester in terms of forces and energy and just extends it to straight line motion into the concept of rotational motion, right? We use the analogy of the car going down the road, and now the car is just going around a circle. And so we're extending the concept of linear kinematics into rotational kinematics. Okay, now before I go on with the current chapter, is I want to look back real quick at the energy lab that we did, and the last question I gave you some hints on, and so what this was is you had the ball. Okay, you let the ball start from rest, and then it left the tube here, and in this part of the lab I asked you, what is the speed of the ball? What's V final? Whoops. What's V final when it hits the ground? Okay, now we've already looked at the concept of center of mass. Okay, so what we're trying to find is V final of the center of mass. Okay, and I gave you a hint. I said, does the ball's rotation rate change from when it leaves the tube to when it hits the floor? Okay, so again, we did this lab. This was kind of getting way ahead, but now we're in the chapter where this will make sense. But I kind of talked about that when you let the ball go from up here, okay, that it's not rotating. Okay, so it's not rotating. Okay, now we have the symbol omega for rotational speed, so it's not rotating. And then when you let go, it starts to rotate. So I'm showing it's rotating here, and it goes faster and faster. It gets down the bottom here, then it starts to climb. The rotation rate gets a little bit less. I called omega initial 0. It has some rotation rate here, and that has some rotation rate at point C. Okay, and if the track inside was frictionless, we said it wouldn't rotate. So we'll see that it's actually the static friction force that causes the ball to rotate. So when it leaves the tube at point C, there's nothing in the air that can change the rotation rate. So whatever the rotation rate is at point C, it's the same rotation rate at point D. And we talked about during this lab, and in this current chapter we'll see, that there's a kinetic energy due to rotation. So whatever kinetic energy it has due to rotation here at point C has the exact same, so that's what I have here. So whatever the rotational kinetic energy is at point C has the exact same rotational kinetic energy at point D. All right. So I went up here and I said, okay, I want to find the final speed when it hits the ground. All right. And not doing this with projectile motion. All right. So that means I don't need a coordinate system. Okay. So I have our general go-to expression. Okay, for energy. There's no work done by non-conservative forces. Okay, it's in the air. No energy lost due to friction. So E final is E initial from point C where it leaves the tube to D where it hits the ground. Okay, so I wrote down all my energy terms. I have K initial for rotation, the initial translational kinetic energy, initial potential, this is when it leaves the tube. Okay, and then E final is when it hits the ground. I have the rotational kinetic energy final, I have the translational kinetic energy final, and I have the final potential energy. Okay, so remember the rotation rate can't change in the air. Okay, so the rotational kinetic energy when it leaves the tube is the same as when it hits the ground. Okay, that spin rate doesn't change, and it's the spin rate we're going to see in a little bit that dictates the kinetic energy, the rotational kinetic energy. So these cancel. Okay, those cancel. Whoops. So those cancel. And then all I have left is that term, which is our 1/2 mv squared, that gets us at point C, where it leaves the tube. Initial potential energy, my reference point potential energy was the ground. So initial potential, my initial potential energy is mg times initial height. Okay, the height of the center of mass, that was h2. When it hits the ground, okay, final translational potential energy is that, all right? And then when it hits the ground, the final potential energy, remember everything in the lab was measured to the center of the ball. All those holes in the tube were drilled at the center of the ball. So the center of the ball never makes it to the ground, okay? So Y final is the radius of the ball. So that's what I have up here. So initial height is h2, where it leaves the tube. Final height is the radius. So the final potential energy is mg little r. So masses cancel, and then you can calculate the final speed of the ball. All right. Okay. And remember, for this, for the speed when it leaves, you're using speed number 3 from the lab because that was your most reliable. Okay. All right. So back to this. All right, so we looked at the concept that we took our car, okay, going down a straight road from chapter 2 from a couple months ago, and we took the road and we bent it in a circle. Okay, so instead of calling it circular motion, now we're calling it rotational motion, because you can also think of this as just a wheel, okay, rotating around its axis, okay, or I could draw a little car driving around a lake. So we saw that the linear position got mapped to its rotational counterpart, angular position. Linear velocity got mapped to its rotational counterpart, angular velocity, and same for acceleration got mapped to its rotational counterpart, angular acceleration, okay? So remember our three equations of motion, all right, for a car going down a road, okay? So remember we had equation 1, okay, which said that if I knew the initial velocity, okay, when we did the car back in chapter 2, initial velocity was 0 at the light, but this allows me to find how fast it's going at any time, okay? Again, now I take the road and I bend it in a circle and the car is going around, okay? So instead of asking for what's the speed v of the speedometer, okay, like we did in chapter 2, I'm going to ask what's the rotational speed, all right? So we're going to use the exact same analysis we did in chapter 2 to derive that, okay? So back in chapter 2, we said A is, we said A is dv dt, okay? Multiplied both sides by dt, and then integrate it and got that. We're gonna do the same thing. So we started from there in chapter 2, we're gonna start from there in this chapter. So angular acceleration, time rate of change of angular velocity. Multiply both sides by dt, okay? Now integrate both sides, okay? So, right, and we're doing this with constant angular acceleration, meaning, let's say a wheel is spinning up or slowing down at a constant rate, okay? So if the angular acceleration is constant, alpha comes outside, I integrate dt, right? So this would be alpha, okay, integrate dt, okay? So I have integral of d omega is omega final minus omega initial. The right side integrates to that. Solve for omega final, and that's equation 1. It looks just like that. So that's why if you look on the equation sheet, that one's not on the equation sheet, okay? That one is, okay? So what I want you to realize is for equation number 1, okay, remember this is with constant acceleration, and we're doing rotational kinematics with constant angular acceleration. That v final gets mapped to its rotational counterpart, same for v initial, and A gets mapped to its rotational counterpart, angular acceleration. So everything looks the exact same. So if you know that one or have that one, you can instantly get the rotational equivalent of number 1, okay? So this allows you to find the rotation rate, at some later time, okay? Now, when we had equation 2, there's equation number 2, wrong one. Okay, we had equation number 2. That's equation number 2. Okay, and if you look back in the notes, we got this one by writing v is dx dt and integrating that to get this. Okay, so where we started from that in chapter 2, we're going to start from the same place right there. So instead of velocity is time rate of change of position, angular velocity, time rate of change of angular position. Multiply both sides by dt, okay? Integrate both sides, all right? Now, remember, just when we did this, okay, look back in notes chapter 2, where I have omega, right? Omega is that, right? It's a function of time. So I have to put in for omega right there, okay? And so I have to integrate this term by term. So the first term is I have omega 0 times dt, and I integrate that. So this integrates to omega 0 t. And here I have alpha t. Okay, I'm integrating alpha t dt, which gives me 1/2 alpha t squared. And then this stuff just integrates to delta theta, or theta final minus theta initial. So this gives me equation number 2 written for angular quantities. So instead of asking here, how far is the car down the road at a certain time? Now this tells you how many times something rotated around after a certain time. okay? So it looks exactly like equation number 2, where each linear quantity, x, v, and a, is replaced with its rotational counterpart, theta, omega, and alpha, okay? Now I'm going to spare you the algebra, but if you look back on our earlier chapter, okay, chapter 2, on how we derived equation number 3, okay, it's a big mess. It's the exact same algebra, and out pops equation number 3 for rotational, okay, rotational kinematics. So this one tells you how fast the car is going a certain place. This tells you the spin rate after it's gone a certain angular displacement, okay? So we'll do a problem that involves these. Okay, so continuing on, here's a problem where I have a CD spinning, okay, at 300 revolutions per minute, and it stops in 2 seconds. And I'm asked to find the angular acceleration of the disk. Okay, so again, I showed that this is analogous to we did in chapter 2. Okay, so the numbers don't make sense for the car, but imagine I have a car moving with a velocity, initial velocity of 300, and it says it stops in 2 seconds, so V final is 0, and I'm asking what's the acceleration, okay? And that reminds you of equation 1, okay? But now we're doing this in the rotational world, all right? Okay, so I have a CD spinning at 300 revolutions per minute, okay? So they still sell CDs, and some people still use CDs, so I want to skip one page. I'm going to come back to this. Okay, so I want to look at a 12-inch vinyl record versus a compact disc. Okay, these are not to scale. Remember, the CD is smaller than the record. Okay, so what's the difference between how these things work? All right, so we showed that when you use the record, okay, the vinyl record, that it spins at a constant rate. Okay, so omega is constant. Okay, so the omega is 33 1/3 revolutions per minute. Okay, it's not in the correct units, right? It has to be in radians per time. This is revolutions per minute, but this represents the rotation rate. Okay, it doesn't matter whether you're playing the first song. Okay, so the first song is on the outer part of the record, last song is on the inner part. It always spins at a constant rate. Okay, if you look at a vinyl record, you can see the wiggles more in here, and here the wiggles are all compressed. Okay, that's why it always sounds better out here, and it sounds crappy there. All right, because the what do you call it? The wiggles in the vinyl, the little waves made in the vinyl, the grooves are so close together, you don't get the same sound as when they're wider apart. Okay, with the CD, okay, biggest difference with the CD is that the spin rate is not constant. It actually depends which song you're playing on the CD, okay? And the CD, okay, the first song is on the inner track, last song is toward the outer, okay? And the spin rate of a CD varies from about 200 revolutions per minute to 500, okay? So the record is 33 1/3. This thing goes from 200 to 500 RPM. And the reason is, again, this is an audio CD. Okay, it's not a data CD that you burn your data to a DVD or something like that. Okay, so for an audio CD, okay, here's your little laser head. The laser likes to read a certain amount of data at the same time. So for example, let's say this length here, that length, okay, on the CD, that purple length, okay, let's say this strip, okay, that length of strip, all right, represents 1 second of music. Okay, so this is 1 second of music, all right. So for the audio CD, this strip, okay, that strip of data has to pass by that laser head in 1 second. So the laser wants to read a certain amount of data, okay, which is 1 second of music, okay, at a constant rate. So on the inner song, okay, so for the inner song, this strip of data, that length of data, okay, if it starts here, goes almost all the way around. But for the last song out here, that strip of data only takes up about a quarter way around. It's about 90 degrees, okay? So remember, the angular speed is the change in angular displacement, okay, or that delta theta per time, okay? Now, let's say for the first song, the inner song, that's over here, okay? To play the first song, or to play 1 second, let's say this is 1 second, to play 1 second of music, this thing has to rotate, that purple strip of data, okay, that purple strip of data, for the inner song, goes almost all the way around. So that's a huge angular displacement, okay? But for the last song, okay, the outer song, this same strip of data, okay, only takes up about a quarter of a rotation, or about 90 degrees. So that delta theta is small, right? That's only about 90 degrees. So for the disc to play 1 second of music from the first song, it has to go almost all the way around, okay? But to play 1 second of the last song on the outer part of the disc, it only has to go about a quarter of the way around. So it has to rotate really fast, okay, for the inner song, because it has to take that 1 second of music and rotate almost all the way around. Okay, so that's why the inner part of the CD, okay, the first track is going about 500 revolutions per minute. The outer track doesn't rotate as fast; it's only going about 200. Okay, so go back here. Okay, so that's why I just said this is some intermediate track. It's going at 300 revolutions per minute. Okay, so essentially this is my omega initial. Okay, it stops. That's my omega final, and that's my time. Okay, and I want to find the angular acceleration. That's delta theta. Oops, no, it's not. My angular acceleration, that's my angular acceleration alpha. Okay, so here's the pattern. I have omega initial, omega final, and a time. So that reminds you of equation number 1. Okay, okay, so omega final 0, because it stopped. I know omega initial, that's my 300, but it's not in the correct units. Okay, so this has to be in radians per second. So I took my omega initial, I said in one revolution I have 2 pi radians, and in 1 minute I have 60 seconds. So the minutes canceled, revolutions canceled. Okay, so that's my correct units of omega initial. All right, I solved this algebraically for alpha, and I put in omega initial. Whoops. Okay, put in my omega initial is 10 pi. Okay, radians per second. There's my time, and there's my angular acceleration. Now, what does it mean that's negative? Well, same for the car, right? When this thing's slowing down, velocity is to the right, acceleration points backwards, the acceleration is negative. So here, the angular acceleration should be negative because the disk is slowing down to rest. Okay. Part 2, what's the total angular displacement? Okay, that's delta theta. So number 2, back in chapter 2, would be how far did the car go? Okay, you're looking for delta x back in chapter 2. All right, so I want to know the total angular displacement delta theta. All right, meaning how many times did it rotate, but in the units I want. All right, so that's equation number 2. All right, so I have my initial angular speed. Okay, that's my that's my 300. Okay, but remember I had to convert it to the correct units. There's my omega initial. Okay, there's the time it takes to stop. There's my angular acceleration. Remember, it's putting on the brakes, it's slowing down. Like when you slam on your brakes of your car, your wheels slow down, the rotation rate. And there's my alpha. Okay, so those S's cancel, and I wind up with 10 pi radians. Okay, so that's my angular displacement while this thing is coming to a stop. Now, I could have used equation number 3, okay, because omega final 0, I know omega initial is a number, and I know alpha is a number. So I solved this for delta theta, okay, put in my omega initial, and I wind up with the same thing. So we saw back in chapter 2 that there's usually more than one way to solve some of these problems, okay? So this is what I was asking to find. That's my angular displacement, okay? Now we could ask, how many times does it rotate, okay? Well, if that's my angular displacement, I'm going to change radians to rotations. So I said in 2 pi radians, I have 1 revolution. Radians cancel. So that thing's that rotated 5 times before it stopped.